Okay, so moving on to chapter 6, question 26. Identify the electrophile and nucleophile. For each of the following reactions, draw curved arrows to illustrate how you make bonds and how you break bonds. So let's just go over the two basic definitions that we need to work with here. The first is electrophile, and the second is nucleophile. So the first thing, the easiest thing to do is just break down each one of these words to try to give you an idea of what they mean. If for whatever reason you don't remember what might constitute an electrophile or what might constitute a nucleophile. So going to the phile bit first, that's loving. So electro, loving, whatever electro means, and nucleo, loving, whatever nucleo means. The easiest way to think of electrophile and nucleophile in terms of breaking down this word is electro is electron, so something that is negative, and loving. Okay, so negative, loving, and nucleophile is again loving, again, just as it was before for electrophile, and nucleo is nucleus, and the easiest way to think of this is positive, so nucleo, nucleus. So we have electrophile is negative loving, and nucleophile is positive loving. So what makes something love something else? So this is answered very simply in that if something's an electrophile and it loves electrons, it's going to be deficient in electrons. And if something's a nucleophile where it loves a positive charge, it's going to be deficient in that positive charge. So if something's more negative, it's more likely to be a nucleophile. Something more positive, more likely to be an electrophile. Okay, so let's use this definition to go through these two different examples for question 26, and there are multiple sub-questions here, so I'm just going to do two of them. So the first one is these two reagents, one's the nucleophile, one's the electrophile. So looking here, this is actually quite simple because we have a formal negative for the chlorine and a formal positive for this vinyl carbocation. Okay, so this is obviously positive, so it's going to be negative loving. So this guy is going to be the electrophile, and we're just going to abbreviate that as E+. Okay, there's our electrophile, and then because this Cl- is negatively charged, it's going to be very positive loving. Okay, so opposites attract. So here we have nucleophile, electrophile, and I'll just say nucleophile right here, just as an abbreviation. Okay, so let's look at the second bit of this question. The second bit saying draw curved arrows to illustrate bond making and bond breaking. So in this case, we're just going to the right, and if we were just going to the right, what we're doing is we're forming a new bond between the chlorine and the vinyl carbocation. So if you look over on the right, you can show, or you can see that this new covalent bond's been made. And so basically what you have to ask yourself is how can we attach the chlorine to that particular carbon? So what we're going to have is this carbon right here being this carbon right here. And what we're going to do to form this bond is we're going to use some electrons from the nucleophile. That's the unifying theme for all nucleophiles if we're going to use it to form a new bond. So we're going to use one of these lone pairs. Chlorine, negatively charged chlorine, has 4 different pairs we could use. We'll just arbitrarily use this one on the right. Okay, so we're going to take these lone pairs and we're going to use them to form a bond. So remember our notation whenever we're drawing arrows. We have a base and we have a head of the arrow. So the base indicates where electrons start and the head indicates where electrons stop. So here we are starting electrons at this lone pair and we're stopping them on that kind of pink carbon. Okay, so that's how we would notate that chlorine's forming a covalent bond, a formal covalent bond with this vinyl carbocation right here. So that would be our final product, and this is how we would get there. Pretty simple. Okay, so this is a little bit more difficult. We don't actually have a formal positive and a formal negative to play around with here, but we can have an idea of what's going to be a nucleophile and what's going to be an electrophile by looking at the final product. So here we have triple bond and HBr. And what we're going to form is, again, another vinyl carbocation and Br-. So here we can try to rationalize it by thinking about which of these is going to be our triple bond from the starting material. So we have 1, 2, 3 carbons here, no carbons here. Obviously, these 3 carbons must come from the original triple bond over here. So what we've done is we see that we've broken one of these pi bonds, and we've used them, and we've used it up. Okay, so we've used it up to form a new bond somewhere, but that second pi bond that used to be a triple bond is not there anymore. Also, that bromine is now negative where it used to be positive. So the question you might ask yourself is, well, what's happened to this hydrogen? So here we can actually, you have to remember that there are many implicit hydrogens in these kind of drawings. And so this is one implicit hydrogen that you don't necessarily see. And there are two more on the right. So there's one implicit hydrogen here and one implicit hydrogen here. So then you might ask yourself if there are any implicit hydrogens on this guy, and the answer is no. You can prove that to yourself by doing a formal calculation here by just saying, okay, well, this carbon is valence of 4. We're going to subtract 1, 2, 3. That's going to be equal to 1 for the formal charge. So that means that there can't be any other bond. If there can't be any other bond, there can't be any other hydrogen bond. So we have 2 hydrogens here on the right for the product, 2 hydrogens here on the left for the starting material. So basically what's happened is that one of these hydrogens, this yellow guy, is attached to this intermediate carbocation. Okay, so at this point it seems relatively intuitive to think about, okay, we can draw this dipole moment for HBr. We can say this H is a partial positive, partial negative for the bromine. So we have an excellent electrophile. So something that is electrophile, negative loving. So this is going to be negative loving since it has a partial positive on it. Okay, so let's go ahead and see how we can use this as our overall electrophile, and I'll go ahead and label it as our electrophile. And since we only have 2 reagents, if one's the electrophile, the other one obviously must be the nucleophile. Okay, and now don't get tripped up here by the E plus and Nu minus designation. I'm not actually saying that these are charged, it's just a shorthand to say nucleophile, electrophile. Okay. And it's my own personal shorthand, so some people might not draw Nu with a negative, some people might not draw E with a positive. It's just easier for me to write it out this way. Okay, so let's go ahead and show how we could potentially use one of these pi bonds to form a new carbon-hydrogen bond. So what we're going to end up having is one of these pi bonds, let's just label it green. One of these green pi bonds is going to end up being a carbon-hydrogen bond. Okay, and we're going to end up breaking this hydrogen-bromine bond right here. And these are going to end up on the bromine. Okay, and obviously this bromine has 3 extra lone pairs that I'm not showing, but they're implicit. Okay, so let's go ahead and show this bond breaking and our resulting bond making process. So this is a simultaneous bond making and bond breaking process in this green arrow. So what this is implying is that we're starting electrons on this pi bond and they're ending over here on the hydrogen. So this base is indicating we're breaking this particular green bond, and whenever we're making this new bond, that's what the head of the arrow is showing, is that we're making a new bond between either this carbon or this carbon and this hydrogen. So this is a very good point, that this bond making process is very ambiguous about which carbon we're actually attaching it to. We could either attach that hydrogen to this red carbon or this red carbon, either one. And you don't really know until after you draw the product. Okay, so we already know that we're going to end up putting this hydrogen on this pink carbon simply because of the way that it's drawn. Okay, also due to stability differences between this secondary vinyl versus primary vinyl. Secondary vinyl is going to be a little bit more stable than primary, so of the two, the secondary vinyl is going to form. Okay, so there's that. I'm just kind of deconstructing this whole process as much as I possibly can. So what we have to do now is you have to ask yourself, is that enough? And the answer is no. If we just stopped it here, then we'd be breaking the duet rule for hydrogen. So again, we can't have more than 2 electrons around hydrogen. You can't do that. Just like the quartet or the octet rule for carbon, you can't break the octet rule. So what we have to do is we keep on going back to this mantra: if you make a bond, you have to break a bond. If you're going to end up breaking either the duet or the octet rule. So in this case, we have to abide by that mantra. Since we're making a bond, we have to break a bond. So we've made our bond, and we have to break this other bond. Okay, so Again, these two, or this lone pair, this orange lone pair for the bromine is coming from this hydrogen-bromine bond. Okay, and that's pretty much where everything's going and where everything's going to, and that should be it. So try to do the other two questions, and we'll move on to the next one.